Everyone, welcome to my channel. Today, I want to show you something powerful. We are going to simulate CT noise starting from projection acquisition, not by simply adding noise to the reconstructed image, but by modeling photon statistics first, and then reconstructing using filter backprojection. We'll compare three cases: noiseless projection, high dose, and low dose. And you'll see exactly where CT noise really comes from. First, we will simulate a noiseless projection. Using this function, this represents the line integral, the true attenuation along each X-ray path. There is no randomness here. This is our mathematical ground truth. If we reconstruct this using filter backprojection, we obtain a perfectly clean image. You can check out my other video, will be in the description, to show you how the detailed steps of generating projections and reconstruction. Now, let's move to the physics. In a real CT system, detectors do not measure line integrals directly. They measure photon counts. The relationship is the measured counts equal to the initial photon counts times the exponential to the power of negative line integrals. To simulate real-world photon detection, it follows a Poisson distribution, so we generate the measured counts using the Poisson distribution around the expected counts. And then we take the negative log to recover the measured projection. And this projection will have noise. To simulate dose variation, we will compare two scenarios. A high-dose case use a large incident photon number, and a low-dose case using a smaller incident photon number. And we will use these two scenarios to simulate both a high-dose and a low-dose scenario, and we will generate three projections. Let's run it. The three projections will be corresponding to the noiseless, which is the line integral and is also our ground truth, a high dose with a higher incident photon, and a low dose with a lower incident photon. We will simulate projections using fan beam geometry, and we will simulate 512 detector counts and 720 view angles. And if you want to see the detailed explanation of how the projection is generated, check out my other video, and I will link in the description. So it will take some time to simulate the three full projection. And when it's done, it will write to our folder. And we will use image J to take a look. Now it is done, and we can see it generates the high dose projection, the low dose projection, and the noiseless projection. Let's get the reconstruction going for the three projections. And this code I have also demonstrated in my other CT physics video. And I will also link in the description below. So now let's get the reconstruction going, and we can take a look at the generated projections using our image J. We will take a look at our noiseless This is our ground truth, and we will also take a look at the high dose. It is similar, and you probably cannot see much of the noise here, but it is the expected counts and added a Poisson distribution to simulate a noisy detected counts. We will also take a quick look at the low noise projection. So from the projection space, it's probably not straightforward to evaluate the noise level. But now let's go back to the image domain. Let's look at the reconstruction noiseless. All images are reconstructed with 512 by 512 matrix. So this is our noiseless data. Let's also look at the high dose. And I'm going to adjust the window and level so we can appreciate the noise better. Let's also open the low dose reconstruction. And let's apply them to the same window and level. So now we can obviously see the difference. The noiseless is very clean because this is pure line integral reconstruction, and this is the high noise simulation, and this is the high dose simulation, which has low noise, and this is the low dose simulation, which has high noise. We can draw a region of interest, and we can compare our noise level. And you can see the high dose is almost similar to the noiseless, while the low dose has significantly higher variance or standard deviation compared to the other two scenarios. So, what did we learn? Noise in CT originates in photon counting. Lower dose means fewer photons. Fewer photons mean higher statistical variance or high standard deviation. And filter backprojection determines how that noise propagates through the reconstructed image. If you truly want to understand CT image quality, you must understand projection domain physics. This simulation shows the full pipeline, from attenuation to photon counting to log transform to FBP reconstruction. You can download the full projection and noise simulation pipeline and try it yourself to deepen your understanding of CT physics. Thank you for watching, and I'll see you in the next video.